So in this video, we're going to take a look at the solubility product, and it is a variation on a theme. It is similar to the equilibrium constant K sub EQ. And to illustrate what it represents, let's consider a cup of water. Let's say you take a glass of water at home, and let's say it's pure water. You might not have pure water at home, but let's say you do. Maybe you could take distilled water that you buy at the store, and you drop into that water a large piece of calcite, large enough that it won't dissolve completely. And you won't need a very large piece because, as we'll see in a moment, that calcium carbonate, this calcite, which is in the solid phase, so that solid is the mineral calcite, it doesn't dissolve very easily into water. It will release a few atoms of calcium, probably more than a few, and that will be in aqueous solution, and then it will also dissolve off into some carbonate ions that are 2 minus and also an aqueous solution. But that equilibrium is not going to go very far. So we can write an equilibrium constant where we take the product of the products. So the products are the calcium and carbonate ions. So concentration of calcium, I'll leave off the 2 plus and aqueous, but just assume that that's this fellow here. And then the concentration of carbonate ion, again, 2 minus, also an aqueous solution. And that'll be divided by the reactants. And we only have one reactant here. And that's the key thing with the solubility product. So we have the concentration of calcium carbonate. And here I will add that exponent S to indicate that it's in the solid phase. If this calcite is pure or nearly so, maybe there's a little bit of magnesium carbonate or iron carbonate that's dissolved in there, but no matter. If it's effectively pure or mostly pure, then this thing is going to be very close to 100%. The concentration of calcium carbonate in that solid phase, if it's 100%, then it's effectively, as a fraction, very close to 1, and so we can ignore it. It can drop out of the equation here, and so we can rewrite the KEQ as just a function of the products, the product of calcium ion and carbonate ion, and instead of calling it KEQ, we call it K sub SP. So that's the solubility product, where we are looking at just the products, and I think that's the origin of the term. We're looking at the solubility of calcite, but here we only need the products rather than the reactants. The reactants really make no difference to us. Now notice that the KSP is only going to work for these special kinds of equilibria, these special kinds of chemical reactions where we just have a pure solid phase as reactants, and we're looking at the aqueous ions, their concentrations in solution. So if we happen to set up an equilibrium that looks like this, pure solid is on one side, and those are the only reactants, and then the aqueous ions that are on the right-hand side, then we can write this this particular form of the equilibrium constant that we call the solubility product K sub SP. To finish off our introduction to this, let's look at some values. So what would be the KSP for calcite? Well, it's about 3.3 times 10 to the minus 9. So that means we have a very small number of calcium and carbonate ions. We'll write the full equilibrium constant again. Remember, these are the 2 plus and 2 minus ions that are in aqueous solution, and then the reactants are calcium carbonate. With this being so small, 10 to the minus 9, it means that most of the calcium and carbonate is bound up here in the solid phase. And this is a typical way of when we would use KSP values. You can find a KSP listed for something like halite, but some people will argue that it's not really appropriate because halite will dissolve almost completely unless you add very, very large amounts to it, and then it also reacts with other things that are in the water, and so the reaction is a little bit more complex. Anyway, the bottom line is you'll often see KSP for minerals that are only slightly soluble. So that's very common to use the KSP for things that are only slightly soluble in water. So a lot of KSP values are going to be very small, but they do vary quite a bit. Even though they're quite small, you can have anything from 10 to the minus 3 to 10 to the minus 40 or something like that. And we'll show some other examples like that perhaps in other videos. And just to finish up here, just now, we've shown that this The amount of calcium and carbonate here must be very low, right? This is much, much less than 1, so most of the calcium carbonate is here in this denominator. Because these tend to be very, very small, looking at minerals that are only slightly soluble, when we have things where the big differences are in the exponents and we don't really care about this value so much over here, then we often take the logarithmic values. So we'll just erase the chalkboard again. So instead of KSP equals 3.3 times 10 to the minus 9, often what we'll do is take the minus log of KSP, and that would be 8.48. And so a lot of times when you look up KSP values, you'll see it listed as a so-called PKSP. So when you see this kind of formulation here with the P in front, that means we're taking the minus log of the KSP value. And if you want to recover the KSP, if it's the actual ratio you're interested in, and you will be, because in another video we'll show how you use that value to calculate concentrations of ions in solution, then to recover that, you would simply raise 10 to the PKSP power. So 10 to the PKSP would be, we'll take 10 to the minus 8.48, and that'll give us 3.3 times 10 to the minus 9. Actually, we'll have to take the minus of that. So we can recover, we can go back and forth from one to the other just by keeping in mind that this, when we see PKSP, it is the base 10 log, not the natural log, which we use pretty much everywhere else in the sciences. It's the base 10 log, the minus base 10 log of the value of PKSP. So you'll see these values a lot. We're comparing PKSP values. I'm not sure why they use the negative value. So when you see large values of a PKSP, it means you're going to have very small values for the KSP. So that's the KSP here that we've recovered as 10 to the minus PKSP value.